Okay, good morning, everyone. So let us start the lecture. We were doing solved problems. So I will continue to do some more solved problems. And then we will discuss CDF, cumulative distribution function. And then we will introduce probability density function. So let us continue with this. So this is the problem that I skipped last time, but I may try to attempt today. So let us say we have two random variables, x and y, that denote the outcome of the roll of two dice. Okay. So we have two random variables, x and y, and then the outcomes is the roll of two dice. Okay. So you can immediately say what is the range of x and what is the range of y. So find range of x and find range of y. Okay, so this should be rather straightforward. So I can, so range of x is 1, 2, 3, 4, 5, 6. And similarly, range of y will be the same because they are the roll of the dice only. So 5, 6. Okay, so the first question is done, and find probability that x is equal to 2 and y is equal to 6. Okay, so and let us see other questions as well. So find probability that x is greater than 3 and given that y is equal to 2, and let z be the sum of x plus y, and then find the range and PMF of z. And the last question is find probability that x is equal to 4 given that z is equal to 8. Okay, so the first few questions are rather straightforward and it's similar to what we did before. But anyway, like let us, it's very simple to note that this is like a simple experiment where you have a roll of two dice. So there is nothing to forget about this. But so what I can do is that I can move to the next page already and start solving this. So let us say, so the first question was done, but anyway, I will write it down. So range of x was 1, 2, and up to 6. And range of y was also 1, 2, up to 6. Okay. And then we want PMF of x, right? So PMF of x is, we know that, okay? So for each of these outcomes, the probability is 1 by 6 for all k in the set 1, 2, okay, to 6, okay? Let's say belongs, and here it's 0, okay, otherwise. And similarly, we can do py k, and that will be same 1 over 6 and k in the set 1, 2, 6, and it is 0 otherwise. Okay, so these are the PMF, and so that's the part A of the question, and part B of the question was probability that x is equal, so this is done, probability that x equals to 2 and y is equal to 6, right? So this is also straightforward from what we know, okay? And so probability that x is equal to 2 and y is equal to 6 is equal to, well, what we note is that since x and y are the roll of two die, they are independent. Okay, so one does not affect the outcome of the other. So this is probability that x is equal to 2 and probability that y is equal to 6. Here, so since x and y are independent. Okay, so from here we know x is equal to 2 is 1 over 6 and y is equal to 6 is also probability is 1 over 6. So this is 1 over 56. So question C is probably find the probability that x is greater than 3 given that y is equal to 2. Okay, so x is so what we want is probability that x is greater than 3 given y is equal to 2. We know that x and y are independent. Okay, so here let us continue here. So since x, y are independent, this implies that probability that x greater than 3 given y is equal to 2 is probability that x is greater than 3. Okay, so occurrence of y has no effect on the, so we are invoking the other property of conditional, right? So if x and y are independent, then this doesn't have any effect. So this is just equal to probability that x greater than 3. So all these things we have done in the class. So here now probability that x greater than 3, right? So now we will look into the PMF. So PMF always serves as a reference for us whenever we are doing calculations. So here we will see x greater than 3 cases are when x is 4, 5, and 6. So this is probability that x is equal to 4 plus probability that x is equal to 5 plus probability that x is equal to 6. Okay, so all these cases are 1 over 6 plus 1 over 6 plus 1 over 6 is 3 over 6, which is half. Okay, so and then D. So D is we are forming a new random variable Z, which is a sum of x and y. Okay, so the first question is find the range and PM of Z. So what is the range of the new random variable that we created, Z, right? So this is nothing but just sum of x plus y, right? So if it's sum of x plus y, then the range will be also sum, like set sum. Okay, so it will be like all what are the all possible sums that you can form and make a set from there. So duplicates should be removed. So range will be starting from 2, 3, because 3 you will get by adding 2 plus 1 and so on. So to do D, we have to find the range of Z. So range of Z is the sum of the set sum of the range of x and y. So which will be 2, 3, 4, and then what is the maximum? We will get 6 plus 6, which is 12. Okay. And now we need to find PMF of the Z. Okay, so this we want to find PZK, where K is from the range, so 2, 3 up to 12. Okay. So what are the, so let us start calculating PZ. Let us say what is PZ2. So PZ2 is probability that Z is equal to 2. Okay, and this is so this happens when, right? So the question is like when is Z is equal to 2, referring to x and y, right? So Z is equal to 2 will happen when, for which values of x and y. Okay, so this happens when probability that x becomes 1 and y also becomes 1, and that's the only possibility for Z is equal to 2 when x equal to 1 and y equal to 1. There is no other thing. Okay, so now it boils down to this, and we know that x and y are independent. Okay, so what we have is probability of Z 2, which is in the previous slide we wrote probability that x equals to 1 and y is equal to 1. And since x and y are independent, probability that x equals to 1 times probability that y is equal to 1. Remember that comma for us is an intersection. Okay, so another way to write this is probability that x equals to 1 as a set intersected with probability that y is equal to 1. Okay, so remember comma for us is an intersection. Okay, so and then we are saying they are independent, so it will be probability of x equals to 1 times probability that y is equal to 1. Okay, so so these values can be calculated rather easily. So this is 1 over 6 times 1 over 6 is 1 over 36. Okay, so that's probability of 2. And similarly, like we have to find all values to compute the PMF of Z. We have to compute all values. So let me do one more. So probability of 3, right? So probability of 3 when for which cases of X and Y it will happen. So this will happen for X equals to 1, Y equals to 2, plus probability that X is equal to 2 and Y is equal to 1. That's the all possible cases, 1, 2 and 2, 1. That's how you will get 3. So again, you apply the independence. So probability that X equals to 1, probability that Y is equal to 2, plus probability that X is equal to 2 times probability that Y is equal to 1. So this is 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6. So this is 1 over 18. Okay. So it's 2 times 1 over 36. So similarly, we can compute probability of Z4, which will be probability that X equals to 1, Y equals to 3, plus probability that X is equal to 2, Y is equal to 2, and plus probability that X is equal to 3, comma, Y is equal to 1. So these are the all possible cases. And then if we compute this, this is 3 over 1 over 36. Okay, so all these cases like 1 over 6, 1 over 6, 3 of those. So this is 1 over 12. Okay, and so on. So now you know how to compute this. So this way we can compute, let us say probability of Z5, it will turn out to be 4 over 36. Probability of Z6, it will turn out to be 5 over 36. So you see the pattern, okay? And then eventually it will start decreasing also. So probability, because for 12 you have only one possibility, 6, 6. So this will be 1 over 6, the last case. And then you have to fill this here. One can verify that, always you should verify to check that your PMF is correct. You should verify that probability PMF sums to 1. Okay, so PMF sums to 1. Okay, so let us say K here. So sum over this K PMF should sum to 1. And then the last case was E, and E question is probability that X equals to 4 and Z is equal to 8. So X equal to 4 given that Z is equal to 8. Remember that Z is the sum of X and Y. Okay, so this is the sum. But since we have found the PMF of Z, there is no, once you have PMF of Z, you can compute any given probabilities, even conditional. So this we apply the definition of conditional. So probability that X is equal to 4, comma, Z is equal to 8 divided by probability that Z is equal to 8. Now the PMF values are computed for this, and they are independent. So X and Z independent. So this is like 1 over 6 times 1 over 6 by 5 over 36. Okay, so this is like 1 over 5. Okay, so this way like we can compute all the probabilities here. Now I have another problem. So I will do like three problems, 3 or 2. Okay, let's see. So so this is the problem where I am given 2 Poisson. So X is the Poisson, Y is Poisson with the parameters alpha and beta. Remember, alpha and beta are the averages given over certain time, and they are given to be 2 independent Poisson variables. Now Z is equal to X plus Y. Okay, be a new random variable. So here what we are trying to see is what will happen if I sum 2 Poisson, and they are independent and they have the parameter alpha and beta. Then what will be the PMF of the sum of the Poisson? Okay, so let us try to solve this. So we note that the range of the random variable X will be like 0, 1, 2, and so on. Okay, and then the range of the random variable Y will be again like 1, 2, and so on. Okay, so it's a count, right? So Poisson, the X is a count of something, like count of customers coming in the shop between this and this, count of the number of buses okay, going through certain points. So count, it's a count, so it starts from 0 and it can go up to, up to theoretically it can go up to infinity. So that's why these are the range. And Rz is given to be the sum of x and y. So hence, as I said, I have to sum range of x and range of y, which will also turn out to be 0, 1, 2, and so on. So this is the range of Z. Now what we are asking for is PMF of Z. So what we need is PMF of Z K. So this is the same thing as saying that, so this is like PMF probability that Z is equal to K. Now Z is x plus y. Okay, so this is the same thing as saying that probability that x plus y is equal to K. Right. Now what we can do is that we can invoke the law of total probability. And what does the law of total probability say? So this is I equals to 0 to K, probability that x plus y is equal to K, given that x is equal to I, and probability that x is equal to I. Okay, so this is we expanded this using law of total probability. So this is law of total probability. Okay, so yeah, so we will continue further in the next. Yeah, so let us do it here. So what we have is so that sum will be equal to I equals to 0 to K, probability that. So what I can do is that the sum that I'm doing is over I, right? So x for the moment is I. Okay, in each term, if I see here, I have I equals to 0 to K. So x is given to be this. So I can fix x to be I here, and I can move that I here. Okay, so let us do that. So that will give us probability that y is equal to K minus I. Okay, given that x is equal to I, and probability that x is equal to I. Okay, so now we also note that x and y are independent. So x, y independent. So this implies that so this thing will go away because x and y are independent. So this is equal to sum of I is equal to 0 to K, and probability that y is equal to K minus I. Okay, and times probability that x is equal to I. And now we can plug in the because these are PMF of Poisson, so I can plug in the PMF. So I equals to 0 to K, and this is K minus I. So since this is K minus I, this will be, and this will be, so this is Y. Okay, so the parameter for the Poisson Y was beta. So this is minus beta, and beta to the K minus I, and K minus I factorial. You have to remember this distributions by, I mean, you have to memorize this, okay, for exams. We will not tell you in the exam. So you have to know all these distributions and what is their form. Okay, and then we have e to the, so this x was with alpha, so this is minus alpha, and alpha to the I divided by I factorial. Yeah, so here constants which are independent of I we can take, and we notice that this is independent of I and this is independent of I. So this is like E minus alpha plus beta. Okay, and then sum I equals to 0 to K, and then alpha to the I, and beta to the K minus I divided by K minus I factorial, and then I factorial. Okay, so we have just written these things. Now this is e to the minus alpha plus beta divided by k factorial. Okay, and inside, if you notice, what I have done actually now is that I have, you see here I see k minus I factorial and I factorial. So if I put a k factorial here on the top, then my plan is that if I put a k factorial on the top here, then k factorial by k minus I factorial, that will be like k choose I, and this is the sum alpha I beta k minus I. So this will give me the binomial expansion of alpha plus beta to the power k. Okay, so that's what I'm trying to do. So I've divided by k factorial, and then I will put k factorial inside. So I equals to 0 to k factorial by k minus I factorial and I factorial, and then alpha to the I, and then beta to the k minus I. Okay, so this is like k choose I. Okay, so this is minus alpha plus beta by k factorial, and this is k choose I. So I put it like this, alpha I and beta to the k minus I. Okay, so this is e to the minus alpha plus beta and k factorial, and this is expansion of alpha plus beta to the power k. Okay, and what does this mean? You see, now you can read out the parameter. This is nothing but Poisson with parameter alpha plus beta, right? So this is Poisson with, so Z follows this Poisson distribution with parameter alpha plus beta. So this is just a yeah, these examples are a way to also show you how you can manipulate things and so on, how you can work with some of the random variables and so on. So these are the practice of those things. Now I guess I have some other stuff now. Okay, so this is some additional problem I have here, where we define the random variable to be x plus 1 whole square. I think I can leave this up to you because this looks rather simple to me. So I don't think I should do this, I think. So this looks rather simple to me. So it's like range of y you can find. Okay, so range of y is just the square of the range of x, and then plus 1, and then square it, and then from there you find the PMF of y. Okay, so this looks okay to me. You can try this. So I will put this in assignment. I have to remember this. Okay, so this I don't see much here. Okay. Okay, so let us do something called cumulative distribution function. Okay, so what we have seen so far is PMF, which is probability mass function. Okay, so here it's a pointwise. You can think of this as pointwise probability, right? So if I throw a die and then the range of x is like 1, 2, 3, 4, 5, 6, and then PMF is the probability that x is at some point, let us say 5, then it turns out to be 1/6. Okay, so this is called probability mass function. So it's like pointwise probability that you do, and this makes sense. So this makes sense for discrete. Okay, but this doesn't make sense for continuous. So if my range of x is some let us say in the interval 1, 2, and if I define probability that x is equal to 1.5, then then this doesn't make sense, probability mass function, because if I use the frequency based approach, so number is like the count is 1, and then the count between 1 and 2. So this is a closed interval, so it's like there are infinitely many points here. So this will turn out to be 0. So probability mass function, you will see, won't make much sense. But what will make sense is if you calculate probability for certain interval. Okay, so if I ask you to compute what is the probability that x is in, let us say, the interval 1.5 and 1.7. Okay, so these things will make sense. Okay, so then like the length of the interval here you can take and then divide by the length of the original interval and so on. And in particular, what will make sense is something which is measurable and it has some length, concept of length, right? So even if I say, for instance, here, even if I say that x probability that x lies in, let us say, 1.5, 1.7, okay, 1.9. So instead of just 1 point, let us say, even if I am defining it x to be 3 points, but still it doesn't change the outcome. So just having finite numbers and so on, computing the probability of any of these out of these infinitely many is always turning out to be 0. So we need something different if you want to go into continuous probability. So you can think of cumulative distribution function as a tool to actually allow you to study continuous cases, okay, continuous random variables. So what actually will make sense is something that is measurable, has some length. Okay, so in maths, if you see, there is an area called measure theory. So what we need is a concept of a measure. Okay, so if you were a math student, then you would have been taught probability from measure theory point of view. Okay, so Borel's, ETS, and so on, but we don't go in that way when we are doing it for computer science students. So there is something concept of measure theory and so on. So there are sound way to introduce things, and measure theory is also needed in advanced type of integrals. So you may not have seen this. So more stronger basis for integration is based on measure theory. Okay, so it's like you are integrating on a measurable set domains. Okay, so the integration, the concept of area and so on, you will do it over a measurable set. So I cannot compute an integral over a set which is not measurable, like discrete points. Okay, so how do I integrate over discrete points? Okay, but if someone tells me that, look, there is a measurable set of certain length, then I can talk about, okay, the area under the curve over a measurable set. Okay, so this is a measurable set. Okay, so similar thing is happening here. You need the concept of a measure, and then you can talk about the probability of that interval, which is measurable in some sense. Okay, so point is not measurable on a line. Line is not measurable in a plane. Okay, so there are concepts like this. Okay, so so we need some way to describe a distribution for the continuous case. So one way is like you do this. You don't just study point-wise case, but you study it for random variables taking values up to certain point. Okay, so for example, here I can say, so this will make sense if I say fx, let us say 1.5. Then this is where I'm asking probability that x is less than or equal to 1.5. Now this is making sense because 1.5 is here, so distance from 1 to 1.5 is measurable. Okay, so this probability will make sense because 1 to 1.5. Okay, so if we compute the probability, let us say on this interval. Okay, so 1 to 1.5 will be proportional to the length of 1 to 1.5, which is 0.5, and divided by the length of the original interval, which is 1. Okay, so these things make sense now. Okay, so these things make sense. It's like probability will be half in this case. So that's why we need to define something called cumulative. Like I just don't want to compute point wise or certain things. I want to add up, and the whole idea behind adding up is that I want to get the concept of certain measurable thing that for which I can indeed compute the probability. Unlike in the discrete case, in the continuous case, I do need this. But on the other hand, cumulative also is applicable to the discrete case. Like there is no harm in asking that probability, what is the probability that, in this case, I can ask the same thing, probability that x is less than equal to 3. I think we have done this in some example just now. So this will be sum of probability that x equal to 1 plus x equal to 2 plus x equal to 3. Okay. But the moment you go into the where the range of your random variable is some continuous domain like this, then you have no hope with the PMF. You can only talk about CDF. Okay, so that's the whole idea about this. So all this, so PMF we were using P subscript X, and for CDF we use F subscript X. And so this subscript denotes indicates that this is the CDF of the random variable X. Okay, so and sometimes we may omit this if we know that the underlying random variable is X only. So then we will drop the subscript. The CDF is defined for all X in R. Okay, so the way, for instance, it may be that the random variable range is, let us say, 1, 2, but CDF I can define for all X in R. Okay, the random variable X is only taking values for here to here, but then remaining ones outside this, the probability will be defined to be 0. And outside this, the probability will be defined to be 1. Okay, and let us say inside this, the probability may be something like this. Okay, so the graph of CDF may look like this. So let us say 1, 2. The random variable is only taking non-zero values, let us say here and here. And beyond this, let us say we can define it to be 0. And outside this, we can define it to be 1, because this is always the probability is cumulative, right? So since X is a random variable, if I sum up, then cumulative moment it reaches here, the probability will become 1. Okay, so fx2 will become 1. And beyond that, you can also say fx3. What about fx3? Well, it will also remain 1. Okay, because beyond that, the random variable is not taking any value at all. Okay, so we can define CDF to be for all X in R in a way that fx less than the lowest value of the range is defined to be 0, and then for anything beyond the upper range of the X will be defined to be always 1. So I will define this concretely. Okay, so let us consider an experiment where a coin is tossed twice. Let X denote the number of heads. Then PMF we know. Okay, so this is a discrete experiment. So PMF CDF also makes sense for discrete. Okay, so we can just do that. So probability that X is equal to 0, number of heads, right? So probability of getting 0 heads is 1/4. Okay, so 0 head will be like probability of only tail. So this is like 1/4, and then probability of getting 1 head is 1/2, and then this is this. So if we draw the CDF, so CDF for this experiment, okay. So if we draw this, then this is how the CDF is a function. So this is how it will look like. So you see the way we have defined is like CDF. So random variable is indeed not taking any value beyond 0. So X doesn't take any. So here we define the probability to be 0, because this probability of this event occurring is 0 anyway, right? So this is 0, and then at 0 the probability jumps to 1/4, which is here, and then probability at X equals to 1 suddenly jumps to half. So this bold means that it is taking the value, and this means that it is not taking this value here. Okay, so at 1 the value it is taking is this bold one. At 2 the value it's taking is 1. Okay, and another thing we notice is, so since it is defined for all X in R, it is also defined for values that are here. I mean, these are not the values taken by the random variable X. Remember, random variable X is taking values 0, 1, 2. but the CDF is defined for all real values along the line. In other words, between these values of x, which is let us say 0.5, let us say 0.5 some point here, then the CDF of 0.5 will be probability that x is less than equal to half. Okay, it doesn't make sense from the experiment point of view, like but probability of getting less than equal to half number of heads, which is same thing as probability of getting zero heads. Okay, because they're so it will keep taking these values until here. Okay, so it will be flat, so it will be a step function, that's what I'm trying to say. And then at 1 it jumps, and then probability of taking having heads 1.5 number of heads. This is same thing as asking probability of getting one head, and so that's why these probabilities will remain same, and then suddenly at 2 it will jump, and then it will continue to take on these values and so on. And beyond this, it will keep on taking probability. I mean, fx will be 1 because the probability, it's a cumulative, right? So it's a cumulative, so it is adding up all the probabilities. So in some sense, it's adding up the PMF. It's adding up the PMF. So anything you take beyond this, it's the sum of the PMF is until this point, and then it will always remain 1 beyond that. Okay, because beyond that, because these are the events that are unlikely to happen, so their contribution to the probability from here onwards will be 0. Okay, and contribution to the probability up to here is 0, and you are doing cumulative, and from here to here it's a PMF values, so they will sum up to 1. Okay, so that's what it means here. So beyond this you will get 1 only always, because any probability here is less than equal to that, and then maximum heads you will get is 2. So this will come into picture. Okay, and then another possibility is that you will get 1. So this will add up because it's cumulative. So cumulative means that you have to add up the probability. In other words, you have to sum up the PMF in the discrete case. So if you add up, then we know that from examples of probability that sum of the probabilities should be equal to 1. Okay, should add up to 1. So this is the CDF. So let us look into CDF and the way it is for discrete case. So this is the discrete case. And in the discrete case, we know that there will be jump because there are discrete set of points for which you are computing the probability. So there will be a jump at all those discrete points. So this is the for x is equal to x1, there is a jump, x is equal to x2, there will be a jump, and so on. And these jumps are exactly the probability value that you are computing. So this is exactly the height is probability that x is equal to x1, and this height is probability that x is equal to x2, and so on. Okay, so and then if we do the limit as x tends to infinity, okay, so if we do the limit as x tends to infinity, this will be 1. Okay, because it's cumulative, as I said, and it will sum up the probabilities. So it has to be 1 because sum of PMF is 1. Okay, so this is the graph, and so this is basically a step function. Okay, so let this be the range and assume that this is the ordering. So this is the ordering we have, and CDF is a staircase. Okay, or step function. This is why it's like a stair. Okay, so and probability of x minus infinity is 0. Okay, so probability that x at minus infinity is 0, and CDF stays flat in xk and xk plus 1. So that's what we know. So this is some xk and this is some xk plus 1. So here it is flat. Okay, and this is true. I'm saying in the discrete case. Okay, so right now we are talking about discrete case. So continuous case I will define shortly. Okay, so this is the discrete case, and then CDF jumps at each xk. So CDF jumps at each xk. So this is the xk, the CDF jumps. Okay, and similarly it will jump here and so on. So we can write this. So probability that xk minus fxk minus epsilon will be probability at xk. Okay, so xk minus epsilon. So if I am xk and then Let's see. So let us say k is 2. Okay, so k is 2, then I'm here, right? So x2 minus fx x2 minus fx x2 minus epsilon. So x2 minus epsilon will be just inside, right? So this is like something very small. Okay, so this is like epsilon here. So probability at x2 will be this guy. Okay, so this is like yeah, okay, so this will be like all so probability at x is less than equal to x2 minus, and this is like probability that x is less than equal to x2 minus epsilon. Okay, so probability that x is less than equal to x2. So probability for all these less than equal to x2, and then probability from here onwards. Okay, so this will be the difference of this. Okay, so probability of x2, so this one, and then the probability of all x2 from here to here. Okay, so of all x2 less than equal to x2 minus epsilon. Okay, so from here onwards, which is this guys. Okay, so this will turn out to be probability that x is x2, just the point value that you have here. Okay, and then the remaining previously what you have computed up to just now. Okay, up to just now what you have computed, that will be removed, so you will get the point probability at x2. Okay, that's what it's trying to say, probability that of x2. So if you just remove the epsilon part, just the left part of that, up to now what you have added up, you remove all those, then you end up getting the pointwise value. So this is all this in the discrete case, and CDF is a non-decreasing function. That is very clear because it's cumulative, so it's adding up the probability. So naturally it is a non-decreasing function, very easy to prove. Okay, because this is like probability of x such that x is less than equal to y. Okay, so is this if y is greater than x, then isn't this y here and this is x here? Yeah, so there is something wrong here. Okay, so if y is greater than x, then fx x is less than equal to fxy. So if y is greater than x, then fxy will be greater than fxx. Okay, so that is evident from here, and also from the probability, because this is like sum of probability up to y, and probability are like positive values always. So since y is greater, so it will have more cumulative values than the x here. Okay, so that's also evident, and CDF approaches 1 as x becomes large. Okay, so as x tends to infinity, it's like you as x tends to infinity, then it's like it's becoming the whole of the sample space. So this is like probability of x such that x less than equal to x. Now I'm saying that x tends to infinity. So this means that x less than x. So as x tends to infinity, the set x less than equal to x will be the sample space. Okay, so it's like it will cover all possible cases, and then hence the probability of this will be probability of the sample space. It's tending to probability of the all possible outcomes because x is tending to infinity, so you are allowing all possible outcomes. So it will become 1. Okay, because no event will be left out as x tends to infinity, so all events will be considered. So that will become sample space, and hence it will become 1. And yeah, so probability. So the way cumulative is defined is like this for the discrete case. So we will sum over all xk which is less than x. So probability fxx is sum of the PMF of all xk values until x. So that's what we have defined here. Okay, so for all a less than equal to b, probability that A less than X less than B can be computed from here, because this is cumulative up to B. So it's like asking A, B. So A, B is here. I'm asking for probability here. So I can find CDF here. So CDF will be sum up to here. And then I can find CDF up to here. OK, so CDF up to here and then CDF up to here. So this will be FXB and this is FXA. So to get this, I will subtract FB minus FA. OK, and then I will get probability for this. So we can compute CDF from here. I mean the probability of certain interval from here. OK, so this is for A less than equal to B, probability that X is less than equal to B is equal to probability that X is less than equal to A plus probability that A less than X less than equal to B. OK, so this is what we know. OK, so we from the probability, and then this is nothing but FXB is equal to FXA plus probability that A less than X less than equal to B. OK, so in the case of discrete case, this and this, we have to keep a note on the, they make a difference in the discrete case. They make a difference in the discrete case, right? Because these are the, if I put a equality, then if I put less than, then because these are in the discrete case, it's a staircase form, right? So it's a staircase form. So these are like this. So indeed, if I include this point, then it's taking this value as well. And if I don't, if I have less than, then it will only cumulative, it will add up only up to here. So we have to keep a note on when it is less and when it is less than equal to, especially in the discrete case. So, or for instance, if I have to compute probability that X is less than X, then this will be probability that X is less than equal to X minus probability that X is equal to X. OK, so so for X is equal to X, I can write this as FXX minus, and this is nothing but PXX. OK, so let us see some example of some example of a discrete random variable. And so let us say we have a random variable X with PMF, which is given by this PK is 1 over 2K and so on. And first is like plot the CDF of X. So what is the plot of the CDF of this? OK, so it's a PMF is given, and then what would be the corresponding like CDF? OK, and find the probability that X lies between 2 and X is less than equal to 5. OK, and find the probability that X is greater than 4. OK, so these are the questions we have. And first question is like, is this really a valid valid PMF? Right. So can you like check that this is a valid PMF? So to check that this is a valid PMF, you have to check that the sum is is 1, right? So it's K is equal to 1 to infinity PXK. So this is like sum K equals to 1 to infinity 1 by 2 to the K is 1. OK, so you can check this. To find the CDF, and what is the plot of this? So if we plot this, then the plot of this will look like this. So let's say this is half, this 5 over 8. Yeah, OK, so I have a plot here actually. So this is the plot of that. OK, so you can check that. OK, so this plot is fine. And what is the next question? So find the probability that X is greater than 2 and less than equal to 5. So let us do that. So probability that 2 less than X less than equal to 5. And we can use the previous result. So this is like FX 5 minus FX2. OK, so this is what we have seen. We derived this result. So FX 5 will be how much, right? So fx5 will be the cumulative up to 5, right? So fx5 is sum over 1 over sum of the probabilities over k, and k is equal to 1 to 5 because 5 is included. So this is like 1 over 2 plus 1 over 4 plus 1 over 8 plus so on. Okay, 32 up to 32, right? So if we do this sum, it will come out to be 31 over 32, right? And then minus f of 2. So f of 2 is 1 over 2 plus 1 over 4. So this will come out to be 3/4. Okay, so this will be 7 over 32. Okay, and this is what we have like this is what we have computed using CDF. Okay, so this is like using CDF. Of course, we could have computed it directly. Okay, so if someone gives me CDF, then I could have computed this using CDF. That's the point. Like I could have done this directly as probability of 3 plus probability of 4 plus probability of 5. Of course, we could have done this. Okay, and let us say C. So C was probability that x is greater than 4. So probability that x is greater than 4 is the same thing as probability that 1 is 1 minus probability that x is less than equal to 4. Now, if the CDF was known, then I can write this as fx4. So this is 1 minus 15 over 16, and this is 1 over 16. Okay, so if the CDF is known and PMF is not known, let us say, then these are the ways one can compute the probabilities. Okay. Okay. So okay, so now what I am trying to do is to go into continuous case now. So discrete we have seen. But before that I will motivate the continuous case with an example. So let x be a continuous random. I have not defined continuous random variable, but just assume that it's something with range is continuous. Okay. So let x be a real number chosen uniformly at random. So let x be a real number. Now you see your random variable is taking real number values. So that happens in the continuous case. Usually, like I can also have discrete case with some real number, but in general, in continuous case, we will talk about random variables taking real numbers. Okay, but I may have a discrete set of real numbers, right? So, okay, so point here is like it's taking, I mean, continuous values between some interval a and b. Okay, so here uniformly means that all intervals in a, b have the same length, have the same probability. So let's say x is a continuous random variable, and it's chosen uniformly at random. Okay, so it's chosen uniformly at random, and here uniformly means all. So by uniform we mean that there is no. So let us say a, b here. Okay, so I mean b here. So if I take, it's a uniform, right? So it's a uniform, then it means that for any interval I take, it's if the length is same, then the probability will also be same. Okay, so that's the uniform case. So find the CDF of x. So note that probability that x is equal to x0, because pointwise doesn't make sense in this case, in the continuous case. Uniformly implies that if probability of x lying in some interval x1 and x2 will be the proportional to the length. Okay, that's what uniformly would mean. And probability that x lies in the whole of the sample space. So in our case, this becomes a sample space, right? Sample space. So that's why the probability of x being in any of these. Okay, so that will be like it's like whole of the sample space only, right? So then it's sure to occur. So that's why it's 1 here. So probability that x lies between x1 and x2 will be defined like this: x2 minus x1. So the length of the interval for which we are seeking the probability of a number lying in that interval will be the length of that interval x2 minus x1 divided by the length of the original interval or the sample space. If you go in a higher dimension, then you will talk about area. Okay, what is the probability that that point lies in a circle bounded inside, let us say, some rectangle, which is your sample space S. Okay, so you talk about area, and then in 3D you can talk about volume. Okay, so now you talk about length, area, volume, and then you take the ratio. Okay, so if you so the CDF, if we write down okay, so if we write down the CDF of this, so let us write down. So we know that fx is probability that x is less than equal to x. Okay, so this implies fx will be 0 for x less than a, and fx we know is 1 for x greater than equal to b, because outside that it's whole of the sample space. And for a less than equal to x less than equal to b, we can write fx to be probability that x is less than equal to x. So this is probability that x is in ax. Okay, so but this is like x minus a divided by b minus a. So now we have the CDF value, so now we can summarize. So fx is 0 for x less than a. It is x minus a by b minus a for a less than equal to x less than equal to b, and it is 1 for x greater than b, because after x greater than b it's like the all possible cases, so that will be 1. So if we draw the graph of this, if you plot this, then all of you can see that the plot of this will look like this. So this is x minus a by b minus a function like this. So it's a linear function, and beyond this b is 1, and below this it's 0. Okay, so that's the CDF, and I think with this I will stop, or maybe I will immediately define. So random variable x with CDF fx is said to be continuous if fx is a continuous function. Okay, so you see the difference now. For a continuous case, the fxx, the CDF of a random variable is always continuous for a continuous random variable. Okay, and if that is the case, then it is a continuous it is called continuous random variable. If the CDF of a random variable is continuous, then the random variable is continuous. Okay, so we will see into this in the next class. Okay, so we will spend 3-4 lectures on continuous case only. So we will see integrals, area. So you have to revise calculus a little bit if you have not if you're not familiar with that. So this is where calculus will come. Okay, so revise integrals and so on. Even multiple integrals maybe we will need. Okay, so we will need limits, we will need sequences and series. So a lot of maths will come now. Okay, so with this I will stop, and yeah, have a nice day. Bye.